bolted short-circuit fault current is determined for arc fault calculations using the following steps. Firstly, calculate the symmetrical short-circuit current, which is also referred to as ISC. This is the maximum current that would flow through the circuit if there were a zero impedance short circuit. ISC can be calculated using the formula ISC equals volts divided by impedance, where volts is the voltage of the circuit and impedance is the impedance of the circuit. Secondly, multiply ISC by a factor of 1.6. This factor accounts for the fact that the actual fault current will be higher than the symmetrical short circuit current due to the presence of arc resistance. Thirdly, the result is the bolted short circuit fault current. For example, if the voltage of a circuit is 120 volts and the impedance of the circuit is 1 ohm, the bolted short circuit fault current would be calculated as follows: ISC equals 120 volts divided by 1 ohm, which equals 120 amps. Bolted short circuit fault current equals 120 amps multiplied by 1.6, which equals 192 amps. Bolted short circuit faults are among the most severe types of electrical faults. When a bolted short circuit occurs, the current flow is extremely high, potentially causing significant damage to equipment and posing serious safety hazards. Understanding how to calculate bolted short circuit fault current is crucial for designing safe and reliable electrical systems. The symmetrical short circuit current, or ISC, represents the theoretical maximum current that would flow in a circuit if a zero impedance short circuit were to occur. This value serves as the foundation for determining the bolted short circuit fault current. The formula for calculating ISC is straightforward: ISC equals volts divided by impedance. The voltage in this formula refers to the voltage of the circuit at the point where the fault occurs. The impedance represents the total impedance of the circuit up to the fault location. This impedance includes the impedance of conductors, transformers, and any other components in the circuit. It's important to use consistent units when performing the calculation. Typically, voltage is expressed in volts and impedance in ohms, resulting in current in amps. The factor of 1.6 applied to the ISC accounts for the presence of arc resistance during a short circuit fault. Arc resistance arises from the electrical arc that forms at the point of the fault. This arc resistance limits the current flow to some extent, but its impact is generally less than what might be expected. The factor of 1.6 is an empirical value that has been determined through testing and analysis to provide a reasonable estimate of the actual fault current. This factor helps to ensure that protective devices are adequately sized to interrupt the fault current safely. The final result of the calculation is the bolted short circuit fault current. This value represents the estimated maximum current that could flow during a bolted short circuit fault. Electrical engineers and designers use this value to select appropriate circuit breakers, fuses, and other protective devices. These protective devices are designed to interrupt the fault current quickly and safely, preventing damage to equipment and minimizing the risk of electrical hazards. In the example provided, with a voltage of 120 volts and an impedance of 1 ohm, the ISC is calculated as 120 amps. Multiplying this value by the factor of 1.6 results in a bolted short circuit fault current of 192 amps. This means that in this particular circuit, the protective devices must be capable of safely interrupting a current of at least 192 amps in the event of a bolted short circuit fault. It's important to note that the actual fault current can vary depending on the specific characteristics of the circuit and the fault location. Factors such as conductor size, cable type, and the presence of other loads on the circuit can influence the fault current. Therefore, it's essential to perform a thorough short circuit study to accurately determine the bolted short circuit fault current for each circuit in an electrical system. A short circuit study involves analyzing the electrical system to determine the maximum fault current that could occur at various points in the system. This study takes into account all of the factors that can influence the fault current, providing a more accurate assessment of the potential risks. The results of the short circuit study are then used to select appropriate protective devices and to coordinate their operation. Coordination ensures that the protective devices operate in a manner that minimizes the impact of a fault on the electrical system. For example, If a fault occurs on a branch circuit, the branch circuit breaker should trip before the main circuit breaker trips. This prevents the entire electrical system from being shut down due to a fault on a single branch circuit. In addition to selecting appropriate protective devices, it's also important to ensure that the electrical system is properly grounded. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip protective devices quickly and safely. Proper grounding also helps to reduce the risk of electric shock. Arc flash is another important consideration in electrical safety. Arc flash is a dangerous phenomenon that can occur during a short-circuit fault. When an arc flash occurs, a large amount of energy is released in the form of heat, light, and pressure. This energy can cause severe burns, blindness, and even death. To protect workers from arc flash hazards, it's essential to perform an arc flash hazard analysis. This analysis involves determining the potential arc flash hazard at various points in the electrical system. The results of the arc flash hazard analysis are then used to select appropriate personal protective equipment, or PPE, for workers who may be exposed to arc flash hazards. PPE can include items such as arc-rated clothing, gloves, and face shields. In summary, determining the voltage short-circuit fault current is a crucial step in designing safe and reliable electrical systems. By accurately calculating the fault current and selecting appropriate protective devices, engineers and designers can minimize the risk of damage to equipment and protect workers from electrical hazards. The steps outlined provide a fundamental understanding of the process, emphasizing the importance of considering factors such as arc resistance and performing thorough short-circuit studies.